Okay, awesome. Yeah, so the past 2 months or so, we've been looking at this BYU locating bacterial flagellar motors competition. And so today I'll just be talking about what the final result was from that, what we learned, the whole process. So um, just the agenda, I'll introduce myself a little bit. I realized at the social I haven't mentioned who I am very much recently, so just most of you know who I am, but I'll at least introduce myself a little bit. I'll talk about the competition, what we were trying to do, and then I'll also talk about some of the characteristics of the problem. So what the kind of angles were that different people took. And then I'll talk about the starter solution because the organizer of the competition actually laid something out that was pretty good. So a lot of people ended up using that. And then I'll talk about the various different tweaks that I made. So along the way, I tried different things and I said, this looks like it's a little bit better. I'm going to do post-processing different. I'm going to model it differently. And so I'll talk about my evolution a little bit. And then after that, the competition just closed and then everyone posts their solutions. And so I'll talk a little bit about what I learned from the things that people posted. So we know what the first through fifth place teams did, and I can kind of find some patterns out of that and then tell you a little bit about what I learned. So just a little bit about me. I've been doing machine learning for like 8 years now, according to my Kaggle profile. So I've been I've been doing it a while in relative terms. I have done a lot of Kaggle competitions over the years. So if you look at my profile, I've actually entered 100 of them. I haven't seriously competed in that many of them, but I've looked at the problem, downloaded the data. I've touched a lot of competitions, and at my last company, I was kind of valued for being a competition grandmaster. So a lot of these competitions were with people from work or with people from meetup, and so I put a lot of emphasis on trying to get good results on that. So I got grandmaster in both competition and discussion. So at one point I was 12th in the world for discussion because I just every time I thought of something I was posting it on the forums. So I was very, very active there. And with the team from the meetup a couple years ago, we actually won the Vesuvius Challenge. So just a few highlights about me. So focusing in on the competition now, what this was doing was we were looking at cryo-ET, these cryogenic electron tomograms. And so what this is it's a 3D scan of some bacteria, basically. So this diagram on the side shows how this roughly works. So they take some bacteria and then they freeze it really, really cold, minus 150 C. And then they do this sort of 3D technique where they can basically tilt it like this, tilt it like that, and then it gives you a 3D view and they're able to reconstruct that back into a 3D volume. So what we were trying to do in this competition was find the XYZ coordinates where these motors were. And I'll show some pictures of what these motors look like in a second. So your bacteria has the flagellum, which is the little tail that kind of drives it around. And then at the base of that, there's the motor that actually moves the little wiggly tail. And so what we're looking for is the motor. So in this data, we had varied resolution. So these images were taken across years, actually. So the scanners got better. We got higher resolution. We got different voxel spacing. So a single pixel would have a different meaning between the different scans because one of them might be very, very small because we've gotten better, higher resolution scans, and one of them might have been kind of coarse because it was an old scan. So this data was curated across years. So there's all kinds of different technology that was introduced. The metric that we were scored against was this F beta score, and the way that they defined it was that true positive, that you got the prediction correct, was that you were within 1,000 angstroms of the label. So it's basically, think of it like if you predicted here and it's 2 nanometers away, then you were close enough, basically. So they counted that as a true positive. A false positive was you predicted a motor when there wasn't a motor, and then false negative was that a motor was actually present and you didn't detect it. True negative saying no motor, you didn't predict anything, so you get points for that. So one thing that I wanted to hop over to was they actually had published a preprint, so talking a lot about this problem, and I wanted to show just some of the diagrams from the paper that they published. Um, so I just want to focus in so we can see some of the details. So like this is what I'm talking about. So this is the flagellum. It's the little tail that drives the bacteria around. Um, and then this in great detail is the actual motor. So if we look over here, it's very hard to see because it's a tiny little thing, but you see the tails going out here, and then at the base here, there's some little structure that's the motor that actually moves the tail around. So digging in, like I was mentioning, there's various different dimensions of images. So you might have something that's 300 slices tall, or it might be 800 slices tall. It might be much bigger, just depending on the scan that they were doing. You have stuff that has very, very different meanings. So you can have something that's a voxel spacing of 6.5. So every voxel is only 6.5 angstrom. So it's very, very small. And then you have something that's almost like 20. So that's 3 times the coarseness, essentially. Um, so the way that the data was formatted was we were given a whole bunch of JPEGs. So the JPEGs are all stacked up, and so it's slice 1, slice 2, slice 3. So we're actually given 2D images, but there's a whole stack of them. So that's what makes up our 3D volume. Here's a diagram showing the true positive, false negative, the stuff that I was just describing. And then we can see some annotations of where the motors are. So in this one, you can see this is actually from the same tomogram. There's multiple motors. So one of the things that I learned throughout this process was that certain bacteria can actually have multiple flagellum, but in a scan, you can also have multiple bacteria. So you can end up with a scan that has 16 motors if you just have a lot of bacteria and they have multiple flagella. From the paper, I think that's all I'll show. So one of the things I wanted to show was I made some videos throughout this process that was basically sweeping through all of the layers. So we have something that's 300 slices and going through, and you can see as you're going through the slices, so going from top to bottom, eventually you'll see the bacteria start popping in, and then at a certain point, you'll see the tail. I added the annotation for the motor, and so you can see that. So we're kind of going through the depth of the bacteria here, and then I'll pause there. So this is the annotation of the motor. So we can see the tail is coming out here, and this is where they annotated the motor. So I made these visualizations kind of as a tool for me to go evaluate the data and understand how is my model doing? How is the labeling done? Is my major problem that I'm not locating them correctly, or is it that I'm not classifying correctly when there is a motor, when there isn't? So I made a bunch of these videos, and it was a very quick way for me to kind of just scrub through, find where the thing is, and then evaluate it based on. So just some characteristics of the problem. So the training set that we had actually had images that had 0 or it had many motors. So it could have 8, for example. But the interesting thing about the test set was they filtered it down to only tomograms that had 0 or 1 motor. So we had this shift between what we were training against and what we were measuring our performance against. And so that caused a lot of interesting problems that people had to solve in order to, how do we train this? How do we measure performance? How do we deal with this gap that we have? So the way that the metric was defined for us, they gave us some code. They said, this is how we're going to score your predictions. And so everyone's using that code, and they say, I'm going to run validation, and then I'm going to see how it performs. But the first problem that most people ran into was when you have multiple motors, this metric isn't designed for that. It would not accept multiple motors. So what most people did is they actually just dropped all of the multi-motor setups. And so that greatly reduced the data because the amount of 0 and 1 motor tomograms was much smaller than we had many that had 2, 3, 4, 5 So we were ditching a lot of data by doing the way that the labels were represented was if we got a -1, -1, -1 for the Z, Y, X coordinates, that meant that there was no motor found. And then if there was motors, then they would mark them Z, Y, X, all of the different motors that were built. So one of the interesting things about this competition that wasn't revealed until partway through when they published the preprint was that many lab members took these images. So they take the bacteria, they freeze it, they do the images, but then only a single one of them did any of the labeling. So that introduces a lot of interesting characteristics because there's not verification. It's not multiple people agreeing, oh, here's where all of the motors are. Motors can be missed, motors can be misplaced. It's not really verified. And that was one of the common themes throughout the competition was everyone's looking at it and they're going, hey, it looks like you missed this one. It looks like you missed that one. This one's marked as a negative, but I see one here. But there were a lot of things that people were trying to figure out in terms of how do we deal with this data being imperfect? And then the secondary problem is if we relabel this, we're improving our training set, but then on the test set, is that going to hold, or is this some like systematic problem that's going to also be on the test set? So if we correct it on the training set, is it actually going to help us on the test set? Or is the test set going to be so different that we don't want to actually do any relabeling? So one of the pieces of this was there was actually very high spatial tolerance. So that 1,000 angstrom threshold, when you look at that, and each voxel is 20 angstroms or 6 angstroms, this is the sort of 3D ball of allowance that was given to you. So you can imagine if your model predicts all the way out here, it's entirely outside of the bacteria, you could still get credit for that. So actually, the localization, the position of your prediction is not that important because you're given such a generous tolerance. It's just a matter of can you classify it correctly and find the ones that have motors that don't. It was pretty forgiving in terms of the position. So talking about the starter solution now, the organizer of the competition gave us a series of notebooks that were going from visualizing the data and then parsing the data and putting it in a format that was ready for training. And then they had a training notebook that was using YOLO V8. And so the way that they formed this was a 2D object detection task. So basically, we have this stack of 3D images, but if we just run object detection on every single slice independently, then we can say this object detection system finds a bounding box where we think that the motors are, and then at the end of that, we say pick the most confident one, and then select that as your ZYX coordinate for where we think that the motor occurred. So just training details. What most people did was they filtered this down to only the tomograms that had motors. So there was about a 50-50 split between tomograms that had motors, tomograms that didn't have motors, and then they just threw away all of the ones that didn't have motors and just focused on the ones that only had one. So that greatly subset the data. And then what they did is they said, we have a single XYZ coordinate, but we know that we can see this motor's layers up and down because you're taking this paper thin slice, and we know that there's visibility of the motors in the layers above and below. And so people introduced this trust factor. So basically said the official label is here, but I'm going to also mark a duplicate label 4 layers up, 4 layers down, and then I'm going to use all of those extra layers as additional training data. So this is an example of one of these stacks. So what we would do is we say this thing is 500 tall, and then we're going to find what the label is, and then we're going to look 1 layer up, 1 layer below, and then this is what one of the images might have looked like. So you have one of the slices, and you say, here's the bounding box where the motor is, and then focus in on that and train against that image. And so the approach that most people did is you do this process, you just sweep it through every single slice, and then you get to the end, and you have to condense all of these boxes that have been output to some final single coordinate, or saying there was no motor at all. So what people did is they said, okay, everything above zero point 0.5, I'll count that as a motor. Everything below zero point 0.5, that's a negative. They just chose some arbitrary threshold or they tuned it. Um, and then of those subset, they say everything above a zero point 0.5, just pick the one that was most confident in order to determine your final VYF. I'll pause. Any questions up to that point? Okay. So now we'll talk a little bit about my solution. So what I started with was just the starter notebook. So I started with the same YOLO 8, and then I made various changes along the way in order to try and improve it. Um, so I used this YOLO as sort of a region proposal system. So I sweep it through all the layers, and then I just say, with a very, very low threshold, just propose all of these areas that might have a motor. That was the only focus at that point. I don't care if I have a whole bunch of false positives, just say anything above zero point 0.1 or 0.01, just include that as maybe there's a motor here. And then one of the modifications that I made was that what some people were doing was only focusing on the images that had motors. I had the ones that had 0 motors. I sampled in some random frames from those. And then I had the ones that had 1 motor. I used those. And then I had all of the multi-motor ones as well. I had to modify the code a little bit in order to handle multiple motors at a time. So at that point, I was using all of the data in some capacity. So one of the things was, if you actually look at it, we have 270,000 slices of images, but then when you did that subsetting, you end up with only 20,000. So you're reducing that number very greatly. And so you also have to balance between the positives and the negatives. If you include all of the other slices as negative, then your model just gets completely washed out because it's just saying everything's a negative because you have so many more negative slices than you do positive slices. So moving on from the YOLO region proposal model, then what I ended up building was a 3D ResNet. So ResNet is the kind of standard image classification thing. So typically it just takes a 224 by 224 image of a cat and it says this is a cat. What I did is I took those weights and then I inflated it to 3D. So this is kind of a common technique. People are able to take the pre-existing weights and say, okay, it was 2D convolutions, make it 3D convolutions, and whenever I need to, just copy the weights to all of the extra layers. So expand them to the dimensions that I need. And this turned out to be very powerful, but I only found this out like pretty close to the end. So then with this second system, I just go through and I kind of re-verify the first system. So the first system is just propose a bunch of regions that it might occur. And then with the second system, I'm saying grab 16 depth, 128 by 128, and then just classify, is there a motor here or not? And that's a coarse enough view that it has extremely high recall. So it's looking 16 layers deep and such a wide crop around it that it has very high recall. So even if you're doing multiple predictions around it, it's going to capture it because it's such a wide range. So even if your original first layer system was off by a few Z's or off on the localization, it doesn't matter because it's looking at a big enough.
It's about something you said earlier, but I only just sort of processed it. When you went through YOLO and you were essentially doing it as region proposal, did you have overlapping regions sometimes?
Yeah.
And so did you accept those or did you do something to eliminate the duplication?
I originally had some deduplication logic. So I would say on a given slice, I can only the center has to be at least 16 pixels away. And I was using that process for a while, but I was realizing it's actually informative. If you have a lot of overlapping predictions, then that gives extra vote to that region. So eventually I removed that. So I had that for a while because it speeds up inference a lot. So if I have a bunch of boxes and they're all kind of overlapping in some way, it's kind of a waste for me to be doing this prediction over and over on a space that's shifted 1 pixel or shifted 4 pixels or something like that. But what I ended up figuring out was that that was extra signal for if the region proposal found 8 boxes all overlapping, just one layer up, one layer down, 4 pixels to the left, and that was extra confidence for that region. So I ended up removing that.
Thanks.
Yeah. Yeah. So this 3D ResNet was a little bit tricky to train because what I needed to do was generate all of these boxes from the first layer model on out-of-fold prediction. So it generates all of these recommendations, and then I have to go through and change the second tier model on top of the first tier model's predictions. So it was a little bit difficult to kind of update that because if I updated the first system, then I had to update the second system in order to get an accurate measure of its performance. But in general, it ended up being very strong. And when we look at the top solutions, that ended up being kind of close to what some people do. So like I mentioned before, the post-processing code that most people were using, at least from the starter solution, was very simple. It was just take the maximum, whatever the max box was, use that as your ZYX. What I ended up doing was a little bit more sophisticated than that. So it's this volume on the right is showing basically the first layer system proposes some regions, and then the second system does all of these 3D predictions. And I told it basically any box that was found, just add that to the total confidence. Any 3D prediction, add that to the total confidence. And then you end up with this sort of localized 3D box. So you can see my region that I was looking at was from 540 to 660, 480 to 600. So this is the sort of area of interest. And then if you look inside of this, I tried to make it less opaque so you can see inside of it, but there's some region inside of there that has the maximum value. So I basically stacked all of the confidence from all of my models together, and then I said, across all of these layers, across all of these crops, what is the point that has the most overlap? So it's kind of like which point shines the brightest across all of the layers, across all of the pieces. Yeah.
This one was so possible. Was like it's impossible. So how it looks the probability of the homogram family among them.
Yeah. So just that specific crop. So if that crop has motor or no motor. So ultimately all it was doing was the object detection gives me some small region to look at, but its confidence was not well calibrated, was what I found. So if it was 0.3 or if it was 0.5 or if it was 0.7, that didn't necessarily mean with high degree of confidence that the 0.5 was less than the 0.7. And so this was sort of like a re-ranking step where it's like I just overwrote the confidence. And so now my 3D model had very good calibration in terms of if it said 0.9, it was nearly guaranteed that there was actually a motor.
On the process, the graph, or you run it on the whole
On the crops. Yeah. Yeah. So I took 16 depth and then 128 by 128 around the specific. So the tomograms were much bigger than that. I don't think I could have fit that in memory. So this was kind of a good in between of I capture a little bit of depth, I capture good XY coordinates, and I'm able to run through
reduce the number of false positives?
I think it was actually the opposite. I think it got me more true positives. It definitely improved my recall. That was the biggest thing because it made it so that something one of the things that I haven't mentioned was like it's theoretically possible that you have a tail that is like facing directly the camera. And if you're looking at the slice that way, then you're like looking at a slice of paper and you might just not see it. And so the 3D lets you see something even if it's the opposite orientation. So I think it was a very small game, but I think that ultimately it must have been capturing some of the like, this is the wrong orientation. So you can't see it when you only take a slice of that because it was a very small game. I'll show I'll show that in a couple.
I'm just kind of curious, so like, what was your intuition, right, from going from like the YOLO model, in the 2D planes to having that YOLO model, basically suggesting a bunch of, possible places where you had then moving. I'm just kind of wondering, like, where was your intuition that the 2D model could give you candidates and the 3D model could give you, specific signals from like the 3D. Like, how did I kind of like satisfy it?
I think I wanted a direct 3D system, but with that size of volume, it's just not really realistic. And the object detection, the 3D object detection systems are just not that developed. Like the 2D have been like we've really mastered those because they're used for self-driving cars and surveillance and all these other things. People have really mastered 2D object detection systems. And so ideally, I would have just done 3D directly, but this was kind of a hack to get around that, to basically say, I'll use 2D context to then guide where do I focus in terms of 3D. Yeah.
I think also if people haven't crunched the numbers, there's a limited amount of training data to train a 3D model from scratch. And also, if you had run 3D without the YOLO, you could have just done a sweep across the tomogram of all possible like XYZ with some stride, not one pixel at a time, but with some stride. But that still would have been, I don't know, insanely more expensive than if you get whatever 20 proposals from YOLO versus running it on 10,000 locations.
Yeah, so the YOLO system is extremely fast. So I can swipe through all of the slices of an image, and if not a single one has a confidence of over 0.01, then I just skip it because the YOLO system is decent enough that it won't miss something like that. But I can sweep through like the bottleneck in that scenario where I say, look at all 800 slices is just the loading of the images. It's not the model. So I can do it as fast as I can get off of this. So that was very valuable. Yeah.
Bacteria look like an so we able to say, hey, here's the pickle, and now we check for the end, and then eventually rotate 3D. In that classification,
yeah. So the question was if there was any sort of like pre-reconstruction step. So one of the things that I was looking at in that regard is like it would be useful just to find the boundaries of the bacteria. So like we saw in that video, you sweep through and it's just nothing. It's just noise. And then eventually you hit the point and you say, okay, here's the beginning of the bacteria. Okay, here's the end of the bacteria. If you could just chop those pieces off, then you have sort of like a better crop of the bacteria, and then maybe you do something with that. I think that would be useful, but we didn't have any labels or any way to kind of like analytically do that. I'm sure there's some way to do it, but with the data that we had and the labels that we had, I didn't see an obvious way to do that necessarily. Yeah. Yeah.
Seems like you guys read 3D volume big samples and 3D sellers and at the point that really you can still just have a whole bunch of you or anybody else work on that.
One of the things that I did early on was we looked at if you just take everyone's focused on the Z slices, so you just go through the Z slices. And so one of the things that I looked into was what if you go across the X axis? What if you go across the Y axis? And those images ended up looking significantly different. And for whatever reason, it seemed like generally the bacteria was oriented in the way that you could see it well through the Z axis, but not that well through the X or Y. So one of the augmentations that I did though on the 3D system was I had it doing free rotation on every axis. So instead of just taking it statically like that, I would rotate it across X, Y, Z all at the same time. And then I would redo the classification because I knew the motor's still in that volume somewhere. I just have to rotate. So that was one of the augmentations that I did was free rotations. But I didn't necessarily do 2D slice at kind of arbitrary. So the inference was all done on Kaggle notebooks. So it was a code competition. So we had to make a notebook that then ran all of the solution on their compute. But I used a run pod system that had a 4090. So not extreme compute, just a regular desktop GPU.
Yeah. Curiosity. The motor is almost on the same side where the clip is.
Yeah, it's always close to the middle. So that was one of the other things that was interesting was people were figuring out you can have a motor without a tail and you can have a tail without a motor. So they were largely related, but it wasn't guaranteed that one led to the other. So one of the things that I wanted to highlight was the validation strategy that I used. So I mentioned a lot of people were taking this and they were subsetting it just to the single motor tomograms, or they were doing 0 and 1 tomograms. I ended up taking the metric code and modifying it so it could handle multiple motors. And I changed my post-processing code so it also allowed multiple motors through. And that ended up giving me a much better look at the actual performance of the system. So it was very telling that people were originally looking at the metrics in terms of slice level performance. So you say, how well did I capture at every slice if there was a motor there or not? And that's one view, but then you have to aggregate that at the end to the whole volume. What is my final prediction? And so people were then doing it at the volume view. And what they were realizing is when you subset it to just the one motor scenario, that's kind of the easiest case. And so they were getting 96% plus performance and then going to the leaderboard and getting like 0.6 or something like that. So it really wasn't a great way to measure the performance. And so what I ended up doing was including all 0 through many motors, modifying the metric, running it for multiple folds, and then measuring it in that way. And that gave me a significantly better representative look of things. I think one of the biggest things, I only figured that out in the last week or so. If I had found that earlier, I think I would have had better time climbing the hill to better performance, because what a lot of people were seeing were you measure this, okay, it looks better, it looks worse. It was very, very bad signal because a lot of it was just noise. When you only have 648 samples, and your validation set is subsetting that to only the ones with one motor tomogram, you really like it's a very, very rocky space. So one of the things that I looked at was just kind of sweeping across thresholds and understanding what the space looked like. Like how fragile were things? If I set my threshold a little bit too high or a little bit too low, what happened to my performance? So I made these little 2D plots. And so on one axis is my slice threshold. So basically saying if it was above a 0.3, then I include that as a positive. And then the other axis was the cluster threshold. So that thing I was mentioning where it's like all of these overlapping and summing confidence, I could say I need at least 20 points of confidence towards this individual thing. So this is the confidence raw out of the detection system. So just summing all of the boxes and then saying filter it in some way. So it's a little bit small, but this is saying the optimal point was 0.833. And if you look at this hill, it's pretty steep. So if you go the wrong direction this way, you fall off the cliff and you get 0.6. If you go a little bit that way, same thing. If you go along the slice threshold, it's a little bit more forgiving, but still, if you go past 0.4, 0.5, you start rolling down the hill. So the next plot is showing my 3D classifier. So swapping out those confidences with the 3D classifier that I did. And you can see all of a sudden the space is so spread out and so much flatter. So I could massively get the thresholds wrong and still end up with a decent result. So this is saying that the peak is higher. So the other one was 0.833, this one 0.847. But the other one, if I get it a little bit wrong, I'm screwed. If this one, I get it, I can go double, I can go half, and I'm still in a decent spot. So that ended up being very, very important. So in the end, I ended up getting a silver medal in 35th. And one of the things that I'm really proud of is in the competitions that I've seriously competed in, I've never gone down on the private. So the way that it works is there's a public leaderboard. They take some subset of the data and they say measure it against this. And then at the end of the competition, they say measure it on the rest of the data and then see what the score is. The problem is when people see that public score, a lot of people go chase that and they say, this is better. I'm going to move up the hill through that way. And then when they reveal to the private data, they did something that was optimized for the data you could see, but didn't optimize for it generally. So one of the things that I take a lot of pride in is I've always gone up because I always try to do the principled thing in order to make sure that I'm getting generalizable results. And I think a lot of it on mine was actually this difference in this landscape. Other people were picking some arbitrary best peak threshold, and then on the private leaderboard, they were falling off the hill, and my hill was so wide I couldn't really screw it. So now moving on to the top solutions, one of the interesting things was a lot of people throughout the competition were trying 2D UNet. So this is a different way of looking at it. The object detection is saying, I'm going to draw a box, and inside of this box is where I think the motor is. The 3D UNet instead, or 2D UNet either, is looking at all of the voxels or all of the pixels and then trying to score them based on the probability. So it's saying close to 1 if it's high probability, close to 0 if I don't think that this is the motor. And a lot of people early on tried this. I tried a 2D UNet approach and I wasn't able to get it to do very well. So one of the things that a lot of people found was it ends up catching on a lot of random things. So like one of the things you can see in some of the tomograms is like it's close to the boundary of the little dish that they're doing it inside of it. So that lights up the signal very high, and then your UNet would just light up on that corner instead of finding the motor. So it's very difficult to find some peak maximum value. But it was interesting that a lot of people struggled to make it work, but all of the top solutions were using. So the top 3 or 4 are all using some sort of 3D UNet. that's looking at the volume, kind of similar to my classifier, but instead of just saying for the whole volume, is there a motor or no motor? They're saying for every single pixel or voxel, try and score it based on whether there's a motor at that specific location or not. One of the common themes was the external data. So there are online portals where they have more of these scans. And so the first place winner actually went, found that data, annotated it, published it. So everyone had access to this new labeled data. But one of the struggles was, how do we actually use this? Because some of it was at different resolutions. He had resized it to all be 128 by 512 by 512, so it didn't really match the signature of what we were doing. But if you look at the top performers, almost all of them use the external data in some way, and it seems like it helped in some very small 0.01, 0.02, something like that. So it boosted everyone, but it was very difficult for people to even evaluate, did this actually help me or not? Because a lot of people were having validation problems. So they go throw in the external data and then they measure the performance and it went down some value or it went up some value, but it was erratic. There wasn't clear signal that it was actually valuable. So I think that was one of the things where it's like, if you have a very good validation setup, then you could have measured it and said this is better, but it's kind of difficult to say if you don't have it. Yeah.
There is not within the solution. You know about if they used pre-trained encoder for 3D unit, or if it was limited customer.
Yeah, so a lot of them, they mentioned that they essentially wired up some sort of pre-trained encoder system. So the first place guy said he even used ResNet 200. So this massive model that encodes it and then creates some embedding, and then the UNet does the rest of the work. But most of it was some pre-trained system giving some features to the UNet. So I don't think anyone took it from scratch. I think that was part of the problem that people were running into, was they were taking untrained, randomly initialized UNets, and that was causing all of the peaks that were like false positives and random things lighting up instead of the F. So I think that the big thing is like getting some pre-trained encoder into that format.
And the pixel-wise semantics innovation, which is for like from here to our object detection path, you know how they like probably mentioned that, I'm not sure I got it, how they were able to reproduce those bounding boxes, and if they really needed for submission and so.
It seems like what they did is essentially we formed it as a bounding box, but in reality it was a single point. And what they did was they drew all of the 1000 angstrom ball, and they said predict this whole ball and kind of blur it at the corner. So you want your peak to be the actual center point, and the surrounding points a little bit less. And then they had different methods for how they actually used the UNet. So some of the people did it where they did sort of like sweeping through the Z. They said 3D UNet from top to bottom. The fourth place team, they actually did patches. So they said, okay, take 128 by 96 by 96, and then just kind of sweep it in 3D across all of the different places. So it's kind of similar to mine, except for they just said run it on everything, and I said run it on all of the proposed regions. And then in the end, they just picked the highest point. So they just said whatever had the highest probability, take that as your XYZ location. Does that answer? Yeah. Okay. So the magic key, what I actually think was what really mattered from their solution, was all of the top solutions used quantile thresholding. So if we look back at mine, I'm setting these thresholds and then just applying that to every sample uniquely on its own. So I say this is the global best threshold, but what they did with quantile thresholding was they basically said, I know that the public leaderboard has 55% motors, 45% no motors. I'm just going to sort them by confidence and then say, my 55 most confident, I'm going to make those all motors, regardless of if it's 0.01, if it's whatever, I'm just going to boost that to say motor, and then everything below that. So they always end up with exactly the proportion of motors, no motors that they expected. And it's a little bit like, that's not really good data science because you're saying like, I just know where my distribution is and I'm going to lock it to that. But in the end, that ended up being the most robust solution. They knew what the distribution was going to look like, and then they just matched that instead of the rest of us were trying to say, if we reach this magic threshold, then count it as positive. If we don't reach it, then treat it as negative. So if you look at all of the top solutions, they use some form of this. And that, I think, was the biggest difference. I'm kind of curious with my own solution, if I did the same process, what I would have. I haven't tried a submission with that yet, but my assumption is that I would get a decent boost. Yeah.
So pretty much every Kaggle competition, I see people talk about quantile thresholding. And like you said, it's not really proper data science. If you had a guess, since people typically get 2 submissions, do you think that their other submissions did not use quantile? Because that's putting a lot of eggs in the basket that the hidden test set is going to be split.
I think that in this case, it was a smart thing to do because the organizer actually told us this is a random split. So you know that it's going to roughly end up, your sampling of 28% on the public set is probably good enough to discern it's going to be 55. So going to the top solutions again, there one of the big things was strong augmentation. So what most people found was you get about 30 epochs in and then you start overfitting. So what the first place person said was they basically just hard augment the whole thing. So they're looking at 3D images. They're doing 3D rotations, they're doing flips, they're doing 100% mix up. So mix up is this technique where you basically say, blur this image into this other image and then have the label be like somewhere in between. And so the interesting thing about that, saying that they did 100% mix up, is the model technically never saw an actual clean tomogram. They were doing combinations between that. The other thing that they were doing was cropping and resizing. So I did something similar. Is basically the idea that we know that we have different voxel spacing. So I could crop a 64 pixel region and then resize it to 128, or I could crop a 256 and then crop it back or resize it back down to 128. So they did the same thing with their 3D volumes, and then they make it more robust to the scale. But the big thing is if you look at the top solutions, they really, really hammered the augmentation to make it so they could train for a long time and have lots of different variations. I thought it was interesting that there were some detection approaches that got near the top, but pretty much all of the people ended up doing some form of 3D in order to get that final boost across the line. Like I mentioned, the UNets had a lot of false positives. I think the way that people got around that was having pre-trained encoders that were strong out of the box. One of the approaches that people were trying was directly regressing out the location. So you take the input in and then your output is ZYX or like normalized to 0 and 1, trying to say specifically where the location was. And there were some strong submissions on the public leaderboard from that, but it doesn't seem like they held up to the private leaderboard. So one of the things I wanted to mention was that there was a huge shakeup on this one. Some competitions, we have enough data, we have a clear enough signal that whoever was in 5th ends up going to 4th or 6th, but they're not going to fall 100 spots. In this one, one of the people that ended up ahead of me came up 426 positions, which is a huge shift in the. Um, so just one of the things there.
And there's a chance that they just got a super lucky
Yeah.
threshold.
Yeah, exactly. Like they could have been on the wrong spot on this hill on the public and then landed on the right spot on the private. So it's entirely possible. Yeah, and that's everything I have.
Question.
Yeah.
You participated in many Kaggle competitions. Is it always the case that people who are in telecom, you don't have external data?
It's not, it definitely helps, but the many competitions you just can't get external data. It's like we got this from some lab thing that is nowhere else, or we got this from this specific sensor in this specific spot that you can't really recreate or get more from. So there's a lot of competitions where you can go find extra data, but many of them is not down to that. I think that in this case, the key point to get gold was the quantile threshold. I think that the external data might have helped you 0.01, but the quantile threshold is really the metric.
Just a short question. So you said that you got 35th place, but you got a silver medal. So did you actually get paid for your submission? Like you get is that
No, so the way that it works is there's like it's different on every competition depending on how many people participate. But the bronze is typically like the top 5% or 10%, something like that. And then silver is some subset of that. And then gold is typically around the top 10 or 20 people. And then the prize is like the top 5 typically. The organizers get to define how that goes, but yeah, that's typically kind of what the breakdown is.
All right, I think we're gonna shift gears here. So, are you in the Zoom?
Yes.
Okay, so then I think what I'll do is I will have you unmute, Anya. If you want to just briefly say hi, introduce yourself, and then you can share screen and take it away.
There are questions that we can't
Maybe you can answer those in chat.
Yeah.
Sorry, guys, we're just getting the logistics here.
Okay, so hello everyone. My name is Anna Malerenko, and actually I've been a data scientist for more than 10 years, but it's mostly academic stuff. So I've been doing biology most of the times, but thankful to Ted and Ryan, last year I participated in Kaggle competition where we just utilizes LLMs. And thanks to that competition, I was hired to a position of actual my dream, and I'm like dealing with LLMs right now. So like for everyone who is present here and online, just please participate in all those competitions. They're so valuable. And I'm going to present a small talk about large concept models. It's going to be most like an overview rather than just going deep into the architecture and showing everything about that, because I was really interested in understanding how it's different from LLMs we just very familiar with right now and use it every day. So I just found out lots of information online about LCMs, but unfortunately the information was in that way that they just talked about it, but it was hard to understand how it's actually different with predicting the next token, which we do with the large language models. So there is one publication which was posted by Meta AI last year. I think it's December 2024. So, and this talk is probably mostly based on that.
Yeah, I'm sorry.
Yeah.
Are you okay turning on the camera?
Yeah, sure.
I know you have to like find the Zoom
No. Where is it? Oh, it's here. Sorry for that.
Thank you.
Okay, yeah. So what exactly is large concept model? So large concept models were, as I said, just published by Meta AI. So the difference they are like presented was mostly not based on predicting like autoregressive prediction of the next token, but versus the next token, it's going to be the next concept. And what they mean by concept is it depends actually on what they're working on. So for example, if we're working with a text, it's going to be a next sentence. So instead of like token level, they just say, we are dividing the text into the concepts, meaning sentences. And if it's about the speech, we can do the same with the speech, dividing each concept into the phrases, like also sentences, but provided from speech. And it can also use images. And as a concept, they define whether the whole image itself, or it might be a part or the area from the image. And so what are the key features they presented? So they say that it's explicit hierarchical structure. And what they mean by that is it's actually really close to how we think that people process everything going around. So it's like, for example, let's imagine we are talking about a pool party. So we're saying the whole concept, the whole idea is a pool party. Then we go deep into the details saying, oh, there's going to be 20 people. They're bringing this food, this thing, and how this reasoning happens is in large language models. So it's from the whole idea going deep into the details. And what they meant by modularity they say that there are a couple of modules, and the thing is, all the small modules, they can be swept, they can be exchanged, and they are not dependent on each other. For example, if you want to process image, it can be done in this way, so the module for image is used. If you want to use it for the text, for the summary or like summarization or whatever, it's going to be the module which works with the text, and it can be it's like interchangeable. So the next one is reasoning and abstract language and the model agnostics, which I'm going to talk next about. They utilize the so-called sonar space, which is a representation of a concept, like an embedding space. But the thing is, it doesn't depend on the language, so it's language agnostic. And it also reproduces the speech, the images, and the texts on the same embedding space. And for example, if we are thinking about, oh, there is a cat sitting on a mat, and you see the same image with the cat sitting on this mat, it's going to be the same mapping region in this sonar space. Also, large concept models helps us to work on zero-shot generalization, which means that even the model were never trained of this data, never seen any of this data, it still can perform well because it works with the concepts, not with the tokens. And that's why, because the concepts are so much longer than the tokens, it helps us to handle the long texts. So when I was telling about they present the performance of LCMs, what they've done is they compared this performance with large language models. So there were different explorations of different cores of the model. So they used, I will talk about the cores later, but they used different of them, and they performed that on 1.6 billion parameters. And the data was trained on 1.3 trillion tokens, which is a pretty large model. And then they said that the architecture was scaled to a model size of 7 billion parameters and trained on 2.7 trillion tokens. So, which is really compared to GPT-4 or even GPT, well, we don't know exactly, right, how many parameters are used and how many parameters tokens was trained on, but it's really compared to that. So, how large concept models process data? So there is an input. I'm going to talk about text, but it's the same for speech and for images. So the text is segmented into the some units, which we will call concepts or sentences. And then it just uses the sonar embedded space when it's just embeds the semantic concept. Then there is the core, which process this information from the sonar space. And after that, we get an output, which also can be reconstructed to the human understandable format or can be used as it is, for example, as for classification model. And sure.
The sonar model, that's a pre-trained model that already exists, so they didn't have to do anything.
That's what I was going to do. So okay. Yeah, so sonar model, it already exists. It's not developed by Meta AI, so it's a separate model. It's open source, so everyone can use it. And what is interesting about this model, so it utilizes more than 200 languages, 76 languages in speech, and even it's called American Silent Language. So it's also in here. And this is a training architecture. So there is like a bottleneck, right, architecture. As far as I could understand, what they did is just the speech encoder on the left was actually added to multilingual text encoder. And so this bottleneck was to represent actually represent the sentence embedding. And it's also just trained in that way that, for example, English sentence and French sentence, if they mean the same, they are the same on the sonar space. Yeah, this is I mentioned already about their languages and languages for speech. So what are actually the advantages of this? It maps the text into a really dense conceptual representation. works on lots of languages. And I would say that they say they are still adding them. And it is multimodal, like texts, images, videos, and everything that you can think of right now. And like embeddings are used as inputs for the LCM rather than the raw tokens. So then when we say think about the next step, it's going to be the core component LCM. So Sonar is usually used as an input encoder and output decoder, but as Ted mentioned, it's pre-trained. They also mentioned it can be trained, it can be fine-tuned for any of your purposes, but it's usually there is no need of that because it's already a huge one. And there are different types of LCM cores that can be used. So it's how the architecture looks. So it's input, then the large concept model, and an output. And so I think that, yeah. So for large concept model, it's going to be the core, which are represented in three main architectures. So the base one, it's the most classical one using mean squared error loss. It's very similar to transformer models. So it's like very simple for just text, like let's say predicting the next sentences or the next concept. The diffusion-based model, it's used, for example, the input concept is given as a text, and you're gonna get the image which is describing this text. And quantized LCM is mostly for, as far as I could understand, it tries to, for the base LCM and for the diffusion-based LCM, we are talking about continuous sentence embeddings. And for quantized, it's more about the discrete units. And it may help sometimes, for example, to, if you are given an input as some complaints from a patient, and you not only want to get the diagnosis, but you also want to see how the reason it happened and to get an output in discrete values, this is for what it used. So the base LCM, it's a transformer surrounded with a pre-net and post-net. So how it happens, there is an input here. So it's a sequence of concepts, excluding the last one, which we need to predict. It goes through the transformer model, and then the output is compared to the input using the mean squared error loss function, and it's how it's trained. And for the pre-net and post-net, it's actually the normalization. So it normalizes the concept embedding received from Sonar and maps them to the transformer dimension. And the post-net does the same, but the opposite way. It's a diffusion-based model presented in two types of architectures. The one is more simple one, as we mentioned. For example, we are given a text, a cat sitting on a laptop, and trying to denoising. It just predicts the image, which is going to be the output. And there is a two-tower architecture. So the tower architecture is more complex. It works pretty much the same, but first the input comes into the transformer decoder, and then it goes into the second tower. And I think it's for more complex. I was thinking of like how they used it. They didn't give any examples of that, but yeah, maybe some kind of video recognition or something like that. Yeah, and as for quantized, yeah, it's going to be as a discrete type of model. And I think this one is the most, is the closest to LLMs, how they work, right? To proceed in the topics. So I was thinking about, yeah,
Do you
sure.
mind if I add just a little bit of color
Sure.
here? So if you guys haven't played around with it, it might not be obvious that if you have an LLM and it gets the next token prediction and it gets the word right, but it has a logit of, let's say, 0.6. So like naively 60% likely. And it's by far the most likely next token. Okay?
Mhm.
So on the surface, if we look at that as a discrete distribution, we could say it's fairly confident. It's not like 90% confident, it's fairly confident that's the next token. If you naively turn this into a continuous model, then that means that 40% of your final prediction is coming from all that other stuff.
Yeah.
And so you can't necessarily take an LLM that's used to working on discrete distributions and just say, yeah, let's just throw in this continuous d-dimensional vector and expect it's going to work perfectly. It might work great, but it might be that it actually has to learn different representations than the kinds it learns from discrete data, like the way we do text with vocabulary 550,000. So just want to kind of highlight, like, why did they have to do more of a search space? Is because people have tried various things, and oftentimes, if you just take GPT-2 and you give it some kind of continuous data, like images, it doesn't work well. And so, like the last one you showed, the quantization is actually a way to turn continuous data into discrete.
Yeah, thank you so much, Deb. Yeah. So what I was thinking about, like how LCMs can be actually utilized, it's more like reports and summaries, because it really keeps the idea of the whole text better. And it seems like since it produces the overall interpretation of the whole text, it's easier like to understand the concept of the whole and summarize it well. So also it might be used to multilingual communication because of the sonar space, which like allows us to use so many languages, and it actually follows the third one as an educational tool. You can imagine like a professor at university who is working on any course to present to the student, and it might be it doesn't need to be interpreted into different languages. It's already actually can be written in multiple languages and presented to students who really like understand different languages. So you don't need to translate everything you have, right? It's already there. And that's why it's also can be really nice using for researchers. Like I was thinking about hypothesis. We can embed our data and trying to ask LCM to predict what kind of hypothesis can be built based on this data. And of course, it might be used for improving chatbots, because we most of times see how hard it's, because it doesn't keep the whole context. We know that we have limitation in LLMs for keeping the like to memorize what tokens were sent to the chatbot. So this might be really useful because it can keep the whole context of the conversation. So, but I mean, of course, of having so many advantages, there are still challenges, because it's really complex data. It's really hard to compute, and for training or fine-tuning, it's extremely expensive. And also there are training limitations, because for these types of languages and context, we really need really good labeled data, which is sometimes really hard to get. And also, even though Meta AI presented different metrics to compare with LLMs like Blue and Rouge, it's appeared they just mostly used Rouge L and Blue. It's appeared like in that concept, it's not actually accurate, because it's not appropriate to use for LCMs. We still don't know what would be a nice metric to represent the data and how it works. And here I just put a slide summary of comparison of LLMs and NCMs. So instead of a tokens, it predicts a next concept. And I think I just mentioned most of them, but I really had a nice question online, which I found and seemed interesting to me. When the LCMs were discussed, there was such a remark. For example, why don't we take LLM, and instead of taking the small token as a word or as a symbol, we just take the whole sentence and predict the next sentence, but use it as a token, like an LCMs. But as far as I could understand, the drawback of this is in large language models, since we used on the prediction and we use the distribution, right? The more data we include in one token, the less information we get. So actually, instead of increasing the probability of better predictions the next token, we decreases it, right? Because the whole information which can be used like in self-attention or whatever is hidden inside of one of the token. So it won't work this way in LLM. And yeah, so just I think I was trying to find out how to play with LCMs, but it's appeared it's not publicly available. And I'm really interested in seeing where it leads to, because LLMs appeared, we saw just a huge usage of LLMs everywhere. For LCMs, it was a kind of hype, it just appeared everywhere. And now it seemed like, like the model where you see lots of interest in, and then it slightly decreases and decreases and decreases, whereas there's no information about it, how it can be used. But I know that there is a GitHub repository where you can find an open source port, so you can use it, and you can not maybe train, because it's very hard to train, it's very difficult and expensive, but maybe fine tune and try to use on your own chatbots or agents, and it can be maybe utilized somehow for summarization at least. Yeah, so I think that's everything I had to say about LCMs. Yeah, sure. Okay. Like this. Mm-hmm. Yeah, so so the question is about if there is a new concept, how will it understand it and generalize and summarize it if it's not learned on that? What they say is actually Sonar space is so well trained, so most of the concepts are already in Sonar space. So it's just what they do is they actually find a map to what's already exists in the Sonar space. So even it didn't see this information before, it can easily match it to something that already exists in the Sonar space. So you don't actually need to train on that because it's already like a large, it's huge model pre-trained there.
Just wonder if you actually tried like, different translation, because
No.
it's not conceptual, but it's also like, it's like the language is reflection of the culture, right? So when you actually like translate one language to another, there's another extra layer. So the same concept have different, completely different,
Yeah, I understand. Yeah.
Yeah, so you actually try to wait, see how well it does, because translation is not the easiest it seems, right? Because of the culture. So I don't know if it actually does some metaphors, like it's just the same context. It can be interpreted and be different, different cultures, right? So, I was just curious about that.
Yeah, so the question was about the cultural differences and the language translation. So if we translate from one language to the other, is it really corresponding to each other, and have we tried to do that? So I have never tried myself, but I saw there was a note in a publication. They are not mentioning cultural differences, of course. They just say, they're saying they tried it for medical and legal data, and they say that it's like really accurate and really high.
Legal data is also different from so that's like
exactly, but
conceptual is like different laws.
It's different laws, and it's even like
how can you actually translate that?
Yeah, it's interesting. Yeah, that's a great question.
Just quick comment. I was under the impression that Sonar, like if you say Alice is angry at Bob or furious or what, like that it didn't necessarily do a great job distinguishing. Like it will get the big concept that Alice is mad at Bob, but I don't know that it does the more subtle things. Which is why I think when you were giving some of the examples, it was like, research, like you want to understand the big idea. It's not important the word choice. So it's not like meant for writing a script for a show.
One doesn't necessarily mean the same in another language. So I'm just curious of the application.
Yeah.
Like translated stuff.
Yeah, I don't know.
Like
It's like here on this diagram, right? They say like, oh, the input was all those for 5 sentences. And so it finds a mapping to these 2 concepts. And like, to me, it seems it's very generalized, but it's not really specific, right? So it's probably, that's why I think just LCMs were presented at the end of 2024 and then silence, right? So it's not that great. Because if it was like,
well, it sounds super great.
it sounds right, but it seems like there are many, many drawbacks which we can see right now, maybe haven't find out yet, because like you don't have actually something to play with, right? It's just the GitHub code which you can utilize, but
you have to train
by yourself, exactly. And there's not like ChatGPT, right? Which you can try and compare. So yeah, that's hard to say.
Do you think they were pizza?
I think so. It seems like they are preparing something. I had an impression they are working on something because they haven't released any of it.
I'm curious about the slide. Ask a little bit more. So the word, but the first thing in the input is the words, and how do you recognize like one word they word, like at which part of this versus this sonar
Yeah, it's a great question. So the question is, are words tokenized and which part they're like use sonar? So sonar is used on an input and an output. So all the words, they are split. If it's a text, the text is split into sentences. So if you imagine like we use tokens, here is this sentence embedding instead of tokens. So the takes the whole sentence, send it to the sonar space, and in sonar space, it creates embeddings. Then these embeddings are sent to the core, and it depends on which core you use. It just plays with it somehow. You get an output, and then if you need like human interpretable output, it just decodes back using sonar. If not, you just get the numbers or whatever you get from there.
Okay.
So is the language encoder kind of like sentence per then?
Per sentence. Mm-hmm. No, it's okay.
Do you have an idea or information why they use auto regression and take the next sentence instead of, let's say, using masking like that?
Yeah, I think it's just a completely different architecture because it depends on which core they're using. So like the base, well, I have really an impression like for the base core, they simply took what already exists, like transformer model. They use a transformer model, like didn't create anything new. For diffusion-based model, they also take like, okay, we have diffusion-based models. They just take diffusion-based models. The only difference here is 1 tower, 2 tower architecture. So for 1 tower, it's just like input text and an image on an output. And here's like an input text. It's somehow processed and sent again to the image. They just simply denoise it, right? So it's diffusion-based. So for me, it seems like nothing new was really created here. It's more like utilizing the sonar space in this way. Maybe I'm mistaken, maybe I just missed something, but I really want to know more about that. So yeah,
That's the right, yeah. It's quite obvious. So
which one?
So that's like
on the right?
No,
on the left?
So,
yeah, so they just try to show like, okay, you are given this 5 sentences is the input, and then how yes, summarization.
Well, mine actually, my question will actually kind of probably develop into something.
okay.
But I mean, it's like more like the I'm gonna ask some.
I think that's very interesting. So I'm curious about which, like you mentioned that they use means for your girl as a loss function.
Mm-hmm.
Do you know at which point? Because I know that usually the other like percentage losses.
Mm-hmm. Yes.
Why they chose these variables.
Yeah, they just use different. As far as I can understand, it's actually depends on the architecture. You can use different of them. So what they present as this mean squared error because there is a text input and they predicted the next sentence. So they just actually simply compared the input and output and find the mean squared error between them. That's what they use. But I think cross entropy also could be used because they mentioned, like, while I was exploring not just the paper, but people describing this like, that's why I didn't present it actually, because they just mentioned tons of different functions which can be used. It's like in Kaggle competition, right? You can use like this and that and that. So it really depends on the core they're utilizing.
But I think when they're training the LCM, they're training just the green box.
Yes, exactly.
Okay.
Just the core.
So in fact, so you don't actually have words. You just have sonar embedding in and sonar embedding out, and those are dense, real value vectors. So for dense vectors, you're going to typically use something like MSE because it's not a discrete distribution.
Right. Assign similarities?
Yeah.
Yeah.
I just like to quote about that for like let's say music environments and environments. But I just that's really interesting.
Yeah, right.
Like want to discuss it.
The thing is, just actually the green one is trained, but the blue ones, which is a sonar part, it's frozen, so it's never trained. The training.
Yeah, I think. Sorry, just a quick note. I think on the unit sphere, MSE and cosine are roughly interchangeable. But when you have vectors with magnitude, then MSE is going to tell you it even if they're pointed in the same direction, what they have magnitude. So it depends on whether you think your space lives on the unit hypersphere, or if you think it's a vector space that's using more than just direction, but using the distance from the origin more. So my guess is that most of our dense embeddings are not on the unit hypersphere. Most of them are actually using magnitude as well. And so that's where MSE might be slightly more expensive to calculate, but would give you more signal than just.
Yeah.
Yeah. So that's basically like normalizing everything to unit vectors and then doing. And so it's that normalization, which either is good if you think magnitude is irrelevant, or it's bad if you think magnitude is important.
I'm curious why your intuition would be that the magnitude would be pertinent in these particular embeddings.
So, like, if you just go all the way back to word effect, right? Dense embeddings usually magnitude matter.
Do you think it's because we're not always able to compare things and just to scale them? For example, if we're talking about like the weight of something, we can say that this is larger than this because we know the difference in the weight. But in ways when we don't know this, when there is no specific way of showing how they're different, the magnitude takes place, like cosine similarity.
I would not call myself an expert on this at all. Okay, so I'm on thin ice, but I'm just going to say that if you give a model d-dimensional real numbers, then it can have a concept like age that it represents magnitude, where young is a shorter vector and old is a longer vector. Okay, and so not all concepts need that.
Right, exactly.
Okay,
yes.
but many concepts do naturally work well with that, and so I think you tend to get that. If you wanted to force it, you absolutely can simply normalize all of your outputs to be unit vectors, then calculate loss. And that will force your model to basically live on the unit hypersphere, in which case you will get those, and cosine similarity will then be all in B. That'd be my best guess.
Yeah.
So I have kind of more an open-ended sort of question. So I'm seeing this like, the sonar space, right? And I'm thinking to how the grade how well, a particular set of LLM or agentic or chat answers, it's, you know, a set of predefined answers. And like semantic similarity or something like the word score that might not be, or person might not be robust enough because, you know, it doesn't actually take into account like the changes in phrasing, etc. So I was wondering, given, you know, your research into this particular, you know, subject, where do you think that LCMs, maybe sonar, in general, could be utilized for the purpose of evaluating, you know, I guess what would you call it, LLM-based systems at this point, or, you know.
Yeah, that's an interesting question. I guess, yeah, so you're saying like you utilize the LLM's outputs more,
Or like you
evaluate
utilize sonar or an LCM to evaluate the output of like an agented system, based system, something like
yeah, exactly. Yeah, it seems like it can be, right, but
For instance, I want to understand, and we, what are they actually trying to get when because what you're explaining is they have got a lot of different ways they added the laws and went through with other different they have different languages. So now with so much data it has not very generalized. Right? Nowadays we are trying to get specialized elements, right? Have a finance oriented element, try to really can replace understanding of words. What are they trying to achieve with that?
yeah, that's a great question. So as far as I can understand, what they were thinking more about is they wanted it to be closer to how a person actually perceives information. So it's more like, okay, you look at the information and just you get the overall understanding of the concept instead of just predicting the next token, right? Just it's not predicting, but it's understanding how it works. And so I was even thinking, and just maybe back to the Liam's question. So why don't just we use a sonar and embed it in LLM? So maybe they might be more useful than just use that complex type of architecture. Yeah.
This is as the base and move it some specialized
Yes.
version.
Yes, right.
Like medical version where we created and understand if there's an X-rays or move it to some other domain. Difficult to understand for maybe for the normal person or it can help in those fields, right? It's in kind of
That's exactly was my question because I work in an abbreviation and medical data. So I was thinking trying to utilize as a whole concept, but it seems like we need more specific output like the diagnosis instead of just versus, oh, this is a summary, what happens to a person. So maybe like if you imagine there is a conversation between doctor and patient and LCM gets the speech and give you the summarization, which you usually get after seeing the doctor, right, in the office. So this might be just a perfect fit for that. But for getting more complex data like abbreviations, I don't think LCM can help with this. Maybe on this right now, maybe they can develop something else.
Yeah, I think the big practical consideration is that if your average sentence is, let's say, 20 tokens, okay, then an LCM sequence length is going to be 20 times shorter.
Yes.
And it's going to be faster and cheaper than an autoregressive one token at a time LLM. I think that's the incentive to do the research. This version of LCM 1.0 is nowhere near ready to replace ChatGPT. But if the idea worked, then you might get some LCM ChatGPT that runs 5 times faster. I think that's the main motivation.
Yeah, that's exactly the idea they just presented. So they're saying that it's 10 times utilizing the speed of the LLMs. So I would say maybe the quality is not yet compared to GPT-4 at least, right? Maybe GPT-4 is somewhere, I would say better, but
Yeah.
not sure. They do have a comparison. So they say just when I mentioned they utilized that 7 billion parameters in 2.7 trillion tokens, they compared saying it's a little bit better than, they actually compared to Llama, not to GPT.
It's not their one.
Is their model, right? So
They say better model than us.
exactly. Yeah. So I would say, for example, we know that GPT-4 I know it's not public information, but it says like it's about 100 to 200 billion parameters, and it's about 10 trillion tokens. So, I mean, it outperforms LCM right now. But who knows, right? I'm still expecting to get something interesting out of that. So, yeah.
What's the largest open source LCM model for the race?
Oh,
The group is quadratic. If it's 1/10 size,
yeah.
okay, if you put the track big, if it's a pretty large model, patient side, that's sort of better results. And it's sort of
Yeah, I'm not sure exactly about the scale, but what is an open source right now. But I guess that's what they also mentioned, that it's very computational hard. Maybe that's why it's not still used everywhere. I mean, it's,
I don't remember, but I think you said is they take
it's
7
7 billion parameters and 2.7 trillion tokens, so trained on. I'm not sure if it's though the one which is on GitHub.
Yeah. I don't remember which one's released, but so
Yes.
that's their 7B is equivalent
7
to
billion,
roughly to Llama 3313,
Yes.
whatever 7B
that's what,
size cost.
yeah, that's what they compared to. But they said it was faster, like 10 times faster.
Yeah, just because it's so much shorter.
It's just much shorter.
Right. Last call for questions. Thank you, Anya. All right, we're gonna wrap things here.